Hello everyone, February the 2nd. Alright, this is the second round for today. Let's get to it. Partition array for maximum sum. Given an array, partition the array into contiguous subarrays of length most k. After partitioning, each subarray has their values changed to become the max value of that subarray. After partitioning, each subarray has their value changed to become the maximum value. Okay. Return the largest sum of the given array after partitioning. Test case generated, blah, blah, blah. So we are partition an array with subarray at most of length k. And when doing so, we can change everything inside to the largest value. Okay, so the largest values. So we shall group as many values around the largest value as possible, right? And the best scenario will be, and then we don't overlap them. And it has to be continuous. Okay, so we can, find the largest 500 in length. Maybe we can DP this. Maybe. I don't know. Just try. So for each one, we'll have to partition it inside. Or on the second one, do we partition it? The third one, do we partition it? And the k is 3. So we have a k, right? We have a k. So we can say at each one, we can actually set at each one what is the maximum value. I mean, the maximum value of here is 1, right? Maximum value is here is 2. We can do 15, right? Why we do 15? Because this is 15. It's bigger than the previous one, right? And then we're within the range, so we can change the previous one to 15. Right, next one's 7, it's small, so we can also change to 15. The next one's 9, and then we cannot change to 15. So for each new one, we can decide whether to follow the previous new, whether to follow the previous max or not. We can try that. Right? So we say we have the previous max where its index is, okay? And then we can choose either to follow it or not follow it. So what you're saying is maybe we can have 1, 15, 7, 9, 2, 5, 10. Maybe with our DP can set to dpij, right? Will be the max sum in array all the way to j with all the way to I, okay? All the way to I with the previous max at j. I'm not sure. So like every new one, I have a previous max. So we can compute to see, previous max or the length of the previous max. No. I mean, the position of the previous max does not really work because you don't know if you can include yourself or not. Oh, shoot. Right. You do not know if you can include the previous max or not. That's probably not a good idea, but you still like, I mean, I can keep the previous max, because if I go down, the previous max is, so you have a previous max. Like I say, we have 7, right? I say previously, the max is 15, and its length is 2. So you can choose to include or not. I can choose not, so I can say from 7, right, down, I can compute its max. Well, maybe we should not do this at the moment. Top down is a little bit easier to reason with, right? So if we go top down, let's say dpi is the max of array I towards the end. Okay, reasonable. So we want to find dp0, right? So when we have here, we do want to know the length of the previous, okay? We can know the length of the previous, and then the current one we can choose whether to add to the previous length or not. If we add to the previous, then I shall set myself to the max of the previous, right? You should set yourself to the max of the previous value, right? But there are 2 variables. You need the previous max, and you also need to know the length, otherwise you cannot do. So you need the length, but if you do the length, you will not know. If you do the length, you will not know. That's the thing. If you do the length, you will not know what is the max. Like if you say, okay, I group to the previous, then you don't do the current one, you just jump to the next one, right? Hold on. Well, the max length is k equal to 3, right? Which means as we go through every single position, one of them has to be the end, right? One of them has to be the end. So, or one of them has to be the start of the next one, right? One of them has to be the start. So I say if the current one is the start of the next one, right? Then I can just from this one and then go, I say, okay, I will group 2 or group 3, right? And yeah, maybe that can work. Like when I'm at I consider this is the start, because every single one can have the possibility of being the start, right? So I have a dp I of 7.0, we say, okay, this is the start. And I start just to go k times, right? As I go once, and I do the maximum of this. Now I see. It's the very similar problem we saw before, right? At each spot, I go through k times, and then the sum of these k is deterministic. We just keep going and find a max among them. Right now we can find it, and then we do the dp for the remainder. Okay, that makes sense. Actually, do you want to use Java for this? I think we can. We need a dp, which is going to be int, right? dp equals to new int but I need the length. So I can just say dp, okay? So int n, okay? And then we say here, n equal to array.length, dp equal to new int n, okay? And then we'll define, say private int dp with integer index, okay? And then we can say dp index equal to max sum of partition array from array partition array from array I index to the end, right? To the end. Probably also need int an array as well. And then we can also call this out this dot, okay? We'll call this dot, and then we can also call this dot array with equal to array, and this dot k is equal to k. Okay, and then we do a k as well. Okay, so now when we do the dp, of course we want to know the maximum, right? We want to know the maximum, so we actually should not use, unless we set everything to -1, right? We can set everything to 0, everything to -1. We probably should. We can just say for int I equals 0, smaller than n, I plus plus, and then we do dp, this dot dp. Oh, I cannot do both dp. I think this has to be memo, right? So this will be memo, and then this will be a memo as well. Okay, memo I is equal to array value, so equal to -1. Okay, so -1, right? And then we say if index is equal to n, right? If index equal to n, we just return 0 because there's nothing. If dp, not memo, index is larger or equal to 0, then we return memo index, okay? Otherwise, we're gonna do it, okay? Otherwise, we wouldn't do it. We set memo index is equal to 0. Is the maximum that we want to try to find. Actually, we don't have to set this. We can just start for value from this. So we can say current max is equal to -1, okay? And then for int I is equal to index I minus index plus 1 is smaller or equal to k, this dot k, I plus plus, right? Because this guarantees that I won't go beyond k count. And then we first say current max equal to math.max, current max, and this dot array I. Okay, we get a current max, and then we say memo index will equal to math.max current max multiplied by how many we have done so far. That's I minus index, right? That's I minus index plus 1. This is how many we have called so far. So it would be the maximum of, in fact, I should do the memo index first, right? And then this plus dp dp the next one, which is I plus 1, right? So basically we set the current one, we set to the current max, however many we have, and then we'll plus the maximum of we choose the next one, dp. And then blah, 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 we do all that, and then at the end we'll return mammal index. Okay, so that's the dp function. And then we'll set up all of this, and at the end we're gonna just return dp because we start from 0. Okay, so we're gonna go 28k, and oh, oopsie doozy, this is not the same. Okay, so we'll Control C. All right, let's take a look. That makes sense. Out of bound. That is weird because I already set this. Oh, it's because this is too much. That actually makes sense, right? Should be smaller equal to math dot minimum this dot k and n minus 1. Or this is the length, right? This is the length. Is actually the length shall smaller equal to the minimum of this, and this should be the remaining length, right? So the total length is n, and we're currently at position I, right? So I think the easier way is to do this. So this shall smaller than k, and I shall smaller than this dot n, right? Should be both. Should be both. Okay, so now we run. Yep, I think this is right. So basically this is a dp solution, right? The LeetCode 1043 dp solution, in which we find the max sum starting from any index towards the end. Then during dp we try all possible grouping from index until we exhaust all until we hit the max length of k. For each grouping we try, right? We try we find its sum, its max sum, and record it. We have solved something similar before, twice. So will be on times k, right? On times k. Okay, so we can submit this. We solved the last time a long time ago, but this time is pretty good. Java is fast after compile it. Okay, so we're gonna do so be 3. That is correct. Copy paste this thing, and we're done. And we're gonna try to see how we solved the last time. Last time was a year and 3 months ago. I use a deck. I think it's similar. It's probably similar. I see the current max, right? And then we're trying to go all of them. Current max, yeah, I'm doing this. Temp is whatever the temp and the current max times this plus the dp something, and then j plus equal 1, and then once we're done, we go, yeah, it's the same one, but weirdly I'm using a deck, while here just good old dp, right? Good old dp. Top down should be fairly straightforward. Current max, yes, yeah, it's the same. Current max, you go to this, we go through the whole thing, and then we set. That's very standard solution, I think. I mean, the only thing that's not standard is I set everything here, so I don't have to repeat. And this one will do the dp here. That's okay. O(n) times k. Bottom up, similar. Yep. Okay, so we're done with this, and then we come back to this. Well, this one we have struggled for so long. So long. But I seem to have a new idea. So the new idea is, alright, we're gonna write it one more time. Alright, 3, 4, 2, 5. We definitely cannot find all the paths, but what we can do is at every root, okay, at every root I have all the paths to the leaf. I have all the paths to the leaf, right? So from any root I have the path to leaf. So when I consider 0, I have the path from 1 to 3. I know that. Let's say just this is something I will return, and it won't be, that won't be too bad. That won't be too bad, right? That won't be, so like along the path we will have if we have something like this, right? So in this I collect a 3, 4, and here I collect a 2, 4, and here I collect a 1, 4, right? So now I'm at a 0, and I have all these represented as a bit mask, right? So these are all bit mask. Then at 0, what I need to consider is, because I need to know from 0 to 4, starting from here, if there exists any palindrome possibility. So if I combine 0 with 1, 4, I consider the whole thing, all right? If I want to consider, say, 0 to 3, then I need to do 0 to 4 kind of minus 3 to 4, right? And then we get 0 to 3. So basically I'll get 0 to 4, okay? I get 0 to 4, and then how do I get 0 to 3? I mean, because I have 3, 4, right? So can I do something from 0, 4 and 3, 4 to find out 0 to 3? And everything is exclusive OR, right? Everything is exclusive OR. So basically it's going to be, so 0 to 3 can exclusive OR 3 to 4, right? Shall equal to 0 to 4, right? And therefore 0 to 3 shall equal to 0 to 4 exclusive OR 3 to 4, right? So I can get this, which means if I do 0, 4 exclusive OR 3 to 4, I get 0 to 3. 0 to 4 exclusive OR 2 to 4, I get 0 to 2. And 0 to 4 exclusive 1 to 4, which I get this, which is, that's how we start, okay? So that's how I get like all the paths that's starting from 0. I can do this exclusive OR. And what we want to know, because we have 27, right? I have 27. So the thing we want to know is 0, 3 a palindrome, right? Is it a palindrome? which is asking, is 0 to 4 exclusive or 3 to 4 a palindrome, right? And we know for it to be a palindrome, this has 27 possibilities, right? 27 possibilities, which basically means once I get 0 and 4, right? Once I get 0 to 4, I want to find 0, 3, 0, 2, 0, 1. I mean, 0, 1 definitely one of them, but that's okay. Once I get 0 to 4, I can go through the 27 possibilities, exclusive was 0 to 4, and see if the value exists in any of this in the path that I get. Like, does that exist inside? And of course, this is going to be a counter. So we'll have the bit mask as the keys, and now we have a counter. Now 1, 2, 0 doesn't matter. Right, we have a counter, and we just see the 27 possibility exclusive of 0, 4, right? Exclusive of 0, 4, and whether, right? Whether the whether any of those exists. If it exists, we add this count, right? If not, we don't. And then when we're done, we only add 0, 4 to this counter before we return it, right? And by doing so, we can handle everything on this side, right? On the, let's say, the left subtree, and however many, right? How this is going to be many paths, so we're going to have like an array of these, right? We're going to have an array of these, array of paths, all right? And then for this, you're just going to add this to the thing, and we're just going to return, right? We're just going to return. And now on the other side, I can do the same thing. Now we have the final one is we need to find this. So like we handle this, now we need to find a cross. How do we deal with a cross? The cross means we take some on this side, right? 0 to something. So like we take something like 0 to something on one side, and then we need exclusive of 0 to something on the other side, and then that should equal to 27 possibilities, right? That's equal to 27 possibilities. Now, we can do, because it's different paths, right? There's different paths. Each path needs to be considered differently, right? Each path needs to be considered differently. So once we finish this, on this side, it's going to be a array of counters, right? Array of counters, and each counter means one path, right? And on the other side is the same thing. So now we need is to because it could be any path, right? It could be any path. So do we need to create another thing, another array of counter of everybody? It's not like it could be a counter of everything. It's just a counter of all, right? A counter of all, like 0 to 4, right? We have 0 to 4, 1 to 4, right? We have those. And then how do we find this? How do we find this? The crossing, right? Right now we just struggle with the crossing. Like no crossing, done. I can solve it. But the crossing, how do I handle the crossing one? I mean, I think the array, like, so for all of them, I have the 0 to the leaf. Okay, I have like 1 value 0 to the leaf, 2 values 0 to the leaf. So basically each one, I get the value 0 to the leaf, right? I get the value of 0 to the leaf. And I have value here 0 to the leaf, right? But then what? Yeah, how do I handle the crossing? Basically gonna be like 0 to 4. Let's just say 0 to 4, you do exclusive or something to 4, right? That will get this part. And then exclusive or 0 to 5, and exclusive or something to 5 on the other side, right? And we check if this is one of the 27, right? One something. So 0 to 405 I can compute, but this and this are not, because there are so many and they have so many paths, right? We have different leaves. We have different leaves, and each leaf has a gazillion of this. And we have to go through every single one of these. That is every single one of these, like on the path, is just the keys of the counter, right? So we have to go through the keys on the counter, right? The keys on the counter. I mean, I can have a combined counter. Can we not have a combined counter? A combined counter of everything. Because this is the root, they are common root, so I can have a combined counter of everything, right? It's like we have an array of counters where each value is just a single path. So that is needed to compute if we have a palindrome on this path, okay? And then we have another combined counter with everything from anyone to the leaf, right? We have the combined counter with everything, and that one on this side and that one on this side. And we have this and this. We just need any of this, because it doesn't matter where you end, right? It doesn't really matter, because you just do that exclusive of that. So you do this and you find that exclusive all with, something else, and you try to see if it's in it, right? If it's in it. If it is, then you can say, okay, we found another one. If it's not, and then once we're done, we return three things. The left path, right path, and overall path, or the left overall and the right overall. Dear me, right? And then we just need to do an overall. We need to merge two counters. Which is merge two counters. So I go through and then we merge two counters, which I think it takes on, because because it's just the total number of okay, I guess, I guess. I think cannot be all a counter. because this can have many leaves, so each one is different, so it has to be an array. It has to be an array because I need to know, like, oh, it doesn't have to be an array. I just need to know from my child to everything down, right? I need this 1 4, I need a 1 3, right? So I need that. So in an array of path starting from here, and we need a counter of everything, right? And a counter of everything, and it has to be like each path needs to have its own. Each path needs to have its own, right? Each path needs to have its own. It cannot jumble together, because I cannot do, let's say 0 3, right, on a 1 4. So the return value needs to be an array of paths from a child to the end, okay, an array of that, and an array of counters. An array of counter, no, yes, an array of counter with each counter is a path, right? And it has all the things in it. And then and a combined, everything combined. Do you want to try? This is a freaking complex. But I seriously hope that I hope this might work, but it could be very hard to wrap my head around. Oh, I'm in the Python this thing. I have no intention to Java this. All right, so first things first, we need func tools. Need import IRU cache, right? This is a no-brainer, and we can just call DP, right? Oh, we need to also create. Oh, we need to create a adjacency list, right? But it's a tree. So adjacency list will be a little bit easier to create. Okay, we need to do adjacency list. So matrix adjacency list, right? Equal to what? That should be a default dict, right? It should be a default dict. A default dict with an array. An array will be the child and the string, the character, right? We'll put a child and a character. So once we've done that, we know, like going here, and then we know the left, the right for each one. Okay, so we can say a default dict from collections, default dict. Okay, default dict. So that should be default dict of a what? A list. Okay, I think a list. And then for parent, for P, for IP in enumerate parent. This is what I hate the most. Redo. It will undo a lot of stuff. Okay, parent. And we say if if I is equal to 0, I should go, hold on. Because a 0 is always going to be a parent. So actually I shall just say in range 1 to len parent, okay? And then I know P is parent I probably don't need to do this. And then I say adjacency list, right, parent dot append child first. So child is going to be I, and we're going to do si is going to be the character, which I can just do this, right? Oh, oopsie doozy, that's wrong. Right, so we can do that. Adjacency parent will go here, and then we go through all of them so we get the adjacency list. That's fine. Okay, so now we have adjacency list. Now we also have to have a self dot result is 0. Okay. Now we can do value cache max size equal to none. Okay, that's gonna be a node, and then we're gonna return. I'm actually not return anything. Okay, we're not returning anything. If we're not returning anything, what is LU cache doing here? We're not caching. We're not caching. I just realized it's not caching. There's no caching. And we can just call it DFS, right? We just DFS it. We just DFS it. And we are at a node, right? We're at a node. And we actually need to return stuff. The return stuff is very complex, which I'm not going to write. Okay, so I'm going to just say we are going to return, okay? We will return, what do we return? A tuple of things. The first thing is an array of bit mask of path from node to each how can I say it? Array of bit masks from node to all the leaves in the subtree, right? Okay, that's an array, and then an array of counters where each counter each counter's key is the bit mask of all subtrees, right? Of all subpaths from a child to the leaf to the leaves. Okay, so this is the second one. And the third one is a counter where each key is the bit mask of all possible subpaths from a child to the leaves. This is essentially a merged version. Then why don't you just use this if you want to merge it? Right? It's just a merged version of this. So we merge this, we do it and then pass it on. Like we don't need to, because we have to go through everyone as well. Actually, we don't need this one, right? So we just need an array of bit mask from the node, from node to everything, okay? And then we need an array of a counter where each counter's key is the bit mask of all the subpaths from a child, from any child, right? From any child to the leaves. That's it. That is the tuple we're gonna return. Okay. So, if I mean, we definitely will go try to find if there's anything, right? So we're gonna return first array of bit masks. So direct path. So bit mask direct path. Okay, and then bit mask counter. Bit mask counters is this, and we probably need a counter as well, which I don't think we need this. Okay, so now we have these two. We can say for child in adjacency list node. Actually, no, child and letter, right? And just says, oh, we also need allowed parodies. Allowed parodies shall equal to this with 0, right? And then in fact, this should be the last one. So for I in range 26, right? We're gonna do 1 left shift I. Probably should do this 1 left shift I. That should be fine, right? 1 left shift for I in range 26. So each one, 1 left shift 1, shift 0, 1, 2, 3, 4, 5. Is it to 26 or to 27? To 26. To 26, because I'm in a minus A. So it's, yeah. So 26, so that's 26 of them. And allowed parodies, we're gonna also dot append a 0. Right? In fact, I want to alright, hold on. Yeah. So we go Python 3. What I want to do is do this 1 left shift I for I in range. How about 4? See what we get. 1, 2, 4, 8. That is correct. Exactly what I had expected. Okay, so this is allowed parodies. Right, allowed parodies. Okay, so for child and letter, and then I can do dfs child to get on the left. So we say left direct paths, left counters, okay, equal to, actually no, there's no left, no right. Come on. There's no left and no right. What we get is just the whole thing. Oh my goodness. There's no left, and it's not even a binary tree, right? They didn't even say it's a binary tree, which means each one comes out. Oh god. Oh god, they could have another one. Which means everything needs to be jumbled together. Everything needs to be jumbled together. But then, this and this, this and this, this and this, and this and this. Oh my goodness. My god. So we not only do we have to create a overall bit mask, but when we get all the bit mask direct paths, right? When we get a bit mask direct paths, yeah, bit mask direct paths, bit mask direct paths. So we'll collect all of them. And for each of them, I need to exclusive OR this with someone else. And then we'll go through the whole thing. Everything on this side. Need to handle everything on this side. Oh my god. Bit mask counters. Okay, so the child and the letter, right, what we have. Then I can do DFS. Child, dir paths and child counters. Go to DFS child, right? And then what we can do is not go through the child paths. I can exclusive OR with this to get the current one, right? And that will be the first one, because this is my first child, and I'll get all the paths. Oh Lord. No, we have to go through every of this child. Okay, child paths. We have this, and that's 2. So this one needs both, right? So we shall say for CP in child derived paths, bit mask derived paths. All right, I want you to say current. Don't say bit mask. Okay, so we say bit mask. We have K. Say current. Okay, next dot. Okay. Right, so current direct path shall dot append CP exclusive OR, right? CP from this towards the end, right? That will exclusive OR because I add a new letter, right? 1 left shift. One left shift this letter. ORed letter minus ORed A, which I think is 97, if I remember right. Is it 97? Oh, how do we find it? Ask the table. If I remember right, lowercase a is 97. Yes, it's 97, right? So because everything is lowercase, so minus 97. Okay, so we're exclusive of this, so we get the current path, and actually we shall get the bit mask shall equal to, because I need to use this one later, VF this, actually this, I believe is this, so we do this, paste here, and then we'll do bit mask, all right, the current bit mask, so we add this to it, and then we'll say current counters, and then counter and the path, they're 1 by 1, right? They're matched, which means I shall do, oh my goodness, I shall do for I in range len child direct paths, and we say count child path equal to child direct paths I, and child counter is equal to child counters I, right? And then we do this, which is good, and then this, and this. Okay, so we do this. What happened? Something's not right? Why you... Oh, I forgot the, this. Okay. So now what? Now we need a counter. In the update the counter. How do I update the counter? Well, I update the counter by putting my current into it, right? By putting my current into it. So we say current counter bit mask, okay, plus equal 1. So it's this path, we add this into it, right? We add this into it. And and then what? Okay, when this is done, then we say current counters dot append cc, right? So by doing this, I will grab all the child paths, right? The path bit mask, I'll get it, and then I get the updated counter and I push into the current derived path, and I go through all of them. So now what we have is a current derived path from my root, my node, towards every single leaf, and the counters is also from the node to every single leaf, and I have all of them. Okay, now we can pull this out and we can try to find. So first of all, we need to find the number of palindrome possible by doing on each path, right? On each path. So now on each path, I have this one, right? I have this zero, I have this full thing, and what I want to know is anything within it is. So I use the 27 possible because it's gonna be the full, again, the full path, right? It's gonna be the full path exclusive or any of the child full path, right? When we do that, and then we get the the parity value of anything, right, in it. And then what we do is we check if it is one of the 27, right? If it's one of the 27, so we go through the 27, we use the 27 to, wait, hold a second, how we do this again? So we want to find is 03, we want to find if 03 is palindrome, right? This is what we want to find out. So we say is 03 is 04 exclusive of 34. That's correct if that's palindrome, which means if this is one of the 27, and if we exclusive all this, so we basically say is the 04 exclusive all one of the 27, is it equal to 34, right? So we go through the 27 possibilities, exclusive all 04, and see if the answer is one of those, and then we can add it to the result. Okay, and of course I'm gonna exclusive all 1, yeah, because this is in the counter as well, right? This is in the counter as well, but hold a second, this is in the counter as well, but this exclusive all 1, oh, exclusive all 1, 2, that's, yeah, if it itself is a palindrome, then exclusive all with some of them will be, okay, so I think this makes sense. Okay, I think this makes sense. So basically now we need to find, right, compute count the number of palindrome paths, okay, starting from node, and on one of its paths, right? Starting a node on one of its paths towards some leaf. Okay, this is what we want to do at the moment. So what we do is we'll go through. So for I in range, again, len current. Let's do this. It's the same thing, right? So what we do is we say, again, current path is current this I. Okay, current counter is, you see I'm using the same variable, but earlier is child, now it's current I. Okay, so now with these two, what I'm gonna go is for possible, right? Possible, I can POS, possible in allowed parodies. Okay, possible in allowed parody. I'm an exclusive OR with the CP, and we say self.ret shall plus equal to possible counter possible exclusive OR the current parody, the current path, right? The possible exclusive of this, and this will run 27 times, and then once we're done, we get it, and then we go through all the paths. That's good. Now, next one, we need to count the number of palindrome paths connecting some path, some path on one subtree and some path on the other subtree. So that we need to use this. Oh, it's really hard to see, but basically, actually, I want to do this one more time, right? So we have some paths on here, right? We have some paths, so some path here, we want to connect into some path on here. So what we have, oh my god, we might be duplicating. I mean, here we're duplicating as well, because this path, right, 0 1 2, if I remove 1 2, I get 0 1, and if 0 1 is good, then if I do 0 1 3 and I remove 1 3, then this one gets repeated. You're kidding me. You're kidding me. How am I even dealing with this repetition thing? Dude. This is awful. This is as awful as it can get. Yeah, you get duplicate. You can get duplicate. You get duplicate. I thought that was it. Right? You get duplicate. Because you're doing all the paths. Right? You're doing all the paths. How can we avoid this duplicate? We might be able to avoid this duplicate. We might. Okay? We might. Well, the duplicate happens. It's only happening on... No, it happens. Like if I have like further down here, then this whole thing can be a duplicate. Right? Then it gets really... No. Alright, I'm going to end it right now. And the thing is getting closer and closer to reading the solution. I really have no idea. This duplicate thing. Anyway, I'll deal with this. I'll give it one more shot. Okay, I'll give this one more shot. If it still doesn't work, I'm checking the solution. There's just something I didn't realize, or whatever. The hints are useless because I already use it. I already know the hints. before even reading it. I'll see you guys tomorrow.